Hello and welcome to our next lecture. Today we're talking about the space L2, which is a vector space that contains functions. Just to give you sort of a structure of what we're going to cover today, I'd like to revisit the properties of the vector spaces Rn that we found very useful. First of all, the vector spaces have one defining properties that we can add vectors together and multiply them by numbers. In other words, we can make linear combinations. And by making linear combinations, we can create new spaces that we call spans. We also define norms and orthogonality for vectors, and that's been done through an operation called inner product. Or a dot product. Once you define the inner product or a dot product, you define the orthogonality for your space. And once you define orthogonality, you can start making orthogonal projections. But in order to make an orthogonal projection, you need to have a basis for a subspace. So the concept of a basis especially orthogonal basis was very important in those calculations. Once you define a basis for your subspace, you can start making orthogonal projections. And the reason to do orthogonal projections is that orthogonal projections give us a so-called best approximation from a subspace. I assumed you discussed these things in your linear algebra class. If you have any questions about these concepts, feel free to direct your questions to me. I'll be more than happy to answer them. So just like vectors, functions can be added to each other multiplied by constants. So you can make a new function by taking two already existing functions and adding them together. You can make another function by taking a constant and multiplying another function by it. In doing so, you can start making linear combinations as sums of coefficients times some functions. And I'm going to put k underneath the summation just to say that the summation index is k. Whether or not k runs through a finite set of indices or through infinite set of indices is not very important right now. And we're going to see both cases in our discussion of Fourier series and Fourier transform. We're going to see infinite summations and we're going to see finite summations. Once you make linear combinations and start making infinite sums, then you really can start talking about subspaces generated by all of those sums. So we can define spans of functions to be sets of all possible sums and usually we will span a finite number of functions. And the only thing that's lacking here is the definition of inner product. Once you define the inner product, you will create a space that we're going to call L2 of A, B. That's a space of all possible functions that are defined on an interval a to b, with the property that the norm defined by the inner product is finite. I'm not going to go into details of what kind of functions go into that space. All we're going to concentrate today is the geometric structure of this space, what makes functions orthogonal, and how we can make approximations of functions with linear combinations of basis functions. So suppose I have two functions f of t and g of t that come from the space L2. And if you're wondering, a and b can actually be infinite. So we can have a space L2 defined on 0 to infinity, or L2 defined from minus infinity to infinity. And again, we're going to see both cases once we start talking about Fourier transforms. So the inner product of the function f and g is defined and denoted as those angle brackets around f and g. And that's the operation that multiplies these two functions together with a twist that the g comes with the complex conjugate, and then it integrates all the way through from a to b. The conjugation operation is important, and yes, we're going to deal with the functions that are complex valued, where the conjugation operation is going to make a difference. For real valued functions, this conjugation operation is always omitted, because the conjugation doesn't make much sense for real valued functions. And if you're wondering where this definition might have come from, think about the inner product for two vectors. We multiply the components and then we add together the results of the multiplication. In this case, we multiply together the function values at each t, and then instead of adding them together, because that will be a somewhat impossible sum to compute, will be infinitely many things to add, we apply the integration operation that works like a summation in the continuous case. So in a way, this definition of an inner product is almost the same as the definition you had for vectors from Rn. Once you define an inner product, you define a lot of other things for the vector space. You define the norm, you define the distance, and you also put a definition of what it means for two functions to be orthogonal. So the norm, or a magnitude, of a function f is just a square root of an inner product of a function with itself. And since the function may be complex valued, when you multiply a complex quantity by its own conjugate, you get the absolute value of this quantity squared. And then after integration, you take a square root. This definition is pretty much the same as the definition of a norm for vectors, because for the vectors, the norm is also an inner product of a vector with itself, with a square root applied to it. Once you define the norm, you also define the distance. And the distance is defined in exactly the same way as it's defined for vectors. The distance between two functions is just the norm of a difference between two functions. We can call two functions orthogonal if their inner product is 0. And once we define the orthogonality, we can define orthogonal sets. Is a set of functions, fk of t, that satisfy that the norm of each fk of t is not 0 for each k, and also the inner product of fk with fj should be 0 if k is not equal to j. The range of values for k may be finite or may be infinite, so I'm not going to specify the range of values here. We should understand that once we establish the range of k, these properties should apply for every k and j within that range of indices. If norm of each fk is equal to 1, then we call such a set orthonormal. The word orthonormal is slightly confusing. Sometimes we say normal things when we mean orthogonal. In this case, orthonormal means orthogonal and having norm 1. The inner product of the functions shares the same property as the inner product of two vectors. For example, the Schwarz inequality is still true. The absolute value of the inner product of two functions f and g will always be less or equal than the norm of f times norm of g. And for linear combinations, the norm of a linear combination is always less or equal than the sum of the norms of the components of that linear combination. We're going to show it for the norm squared. So if we have two functions added together in a linear combination, when this is the same as an inner product of this linear combination with itself, expanding this linear combination leads to alpha 1 times alpha 1 bar with the inner product of f1 with itself plus alpha 1 times alpha 2 bar times the linear product of f1 with f2 plus alpha 2 alpha 1 bar times the inner product of f2 with f1 plus alpha 2 times alpha 2 bar times the inner product of f2 with f2. We can bound the terms by saying that alpha 1 times alpha 1 bar is just absolute value of alpha 1 squared, and f1 with f1 in inner product is just f1 with its norm squared. Alpha 1 times alpha 2 can be viewed as an absolute value of alpha 1 times absolute value of alpha 2 times absolute value of f1 with f2. Doing the absolute values of these numbers will only make them bigger, and that's why I have the inequality now. Plus absolute value of alpha 2 times absolute value of alpha 1 times the absolute value of f2 with f1 plus the absolute value of alpha 2 squared times norm of f2 squared. So we can say that this is the same as the absolute value of alpha 1 squared times norm of f1 squared plus 2 absolute value of alpha 1 times absolute value of alpha 2 times the absolute value of f1 with f2 in inner product plus absolute value of alpha 2 squared and a norm of f2 squared. After you apply the Schwarz inequality to the middle term, you will get the following. You can replace the absolute value of the inner product with the product of the norms. Which is simply the square of this sum. Taking the square root will yield a familiar inequality that we call it triangle inequality, that the magnitude of the sum of two vectors is always less than or equal than the sum of the magnitudes. I apologize, I put alpha 1 right here, it should be alpha 2. So what's the meaning of two functions being orthogonal to each other? Well, it's just the fact that this integration results in 0. There is no geometrical interpretation of orthogonal two functions, as there is no way to visualize functions as multidimensional vectors. So let's look at this particular example. When I define a whole set of functions, and as you can see, k runs from minus infinity to infinity, so we have a doubly infinite set of functions. And all I have to show here is that the norms of these functions are non-zero, and that each function is orthogonal to another function. So let's look at the norm of particular phi k. Well, that is an inner product of e to the I 2 pi k t over L with itself. That letter on the denominator is the letter L. Computing this inner product gives us the integral from a to b of e to the I 2 pi kt over L times the complex conjugate, which is e to the minus I 2 pi kt over L dt. As you can see, the powers of the exponential functions cancel each other out perfectly, so we basically have the integral from a to b of e to the 0, which is 1, and this integration results in just b minus a, which is L, and that's not equal to 0. If we try to compute the inner product of any function with any other function, we get an integral from a to b of e to the I 2 pi k t over L times e to the minus I 2 pi j t over L dt. So in essence, it's going to be the integral from a to b of e to the I 2 pi k minus j t over L dt. The antiderivative of this is L over I 2 pi k minus j, and since k is not equal to j, this is not 0, times e to the I 2 pi k minus j t over L, evaluated from a to b. So we get L over I 2 pi k minus j multiplied by e to the I 2 pi k minus j. And I'm going to replace t with b, but I'm going to write b as a plus L. And you're going to see the reason why. Minus e to the power I 2 pi k minus j times a over L. As you can see, the factor a is in both exponential functions. So we get L over I 2 pi k minus j multiplied by, and I can factor out e to the I 2 pi k minus j a over L times e to the I 2 pi k minus j, and L over L is just 1. Minus 1. And this part is equal to 1. Therefore, the result of this dot product is 0. Why is this equal to 1? Well, because we have 2 pi multiplied by an integer, and e to the I theta is a 2 pi periodic function. E to the I 2 pi times any integer is going to be 1, according to the earlier formula. If k is not the same as j, the result of this inner product is always going to be 0. So we have ourselves an orthogonal set. We can make it an orthonormal set if we normalize every single phi k of t. But since the norm squared of each one of those is just L, all we have to do to normalize them is divide by square root of L. Let's look at yet another example of a HR basis. What is a HR basis? Well, in order to show you, I would rather use Mathematica. The first function is just 1 on the interval from 0 to 1. The second function is slightly different. The second function is going to be a step down to -1, then in half of the interval steps up to +1. Let me give you a plot of this function. As you can see, if you multiply this function with the previous one, and if you integrate, the two halves of the function will give us 0 integral. Let's try to see what other functions from this family look like. As the next step, we produce two functions. One that's going to take the interval from 0 to a half and then create this step-like function just on that interval. And as you can see, if you multiply these two functions together that I have, you're going to get this function multiplied by -1. And if you integrate, these two halves will negate each other and create a 0 integral. So the dot product of this with the function I had before will be 0. The dot product of this with the original function that's always 1 is going to be also 0 because it's going to create this function. The next function is going to be the shifted copy of the function I had before. And as you can see, it's also going to be orthogonal to the function I have drawn previously. The next level of these functions is going to be squeezed copies of the function I have before. And as you can see, the width of this interval where this function is non-zero fits within the intervals where all of the previous functions are constant. And all of the shifts of these functions are orthogonal to each other because they're non-zero on completely disjoint domains. And this dot product with the function I have above will be 0 because, again, these domains are disjoint. But as soon as I get to the third function from the set, then I start to get to intersect the domains with the one I have previously. But again, as you can see, this function multiplied by previous function is just going to create a negation of this function. And this is still going to integrate into 0. So this function is still orthogonal to the previous one and to the previous one. The Haar basis is also known as the simplest form of wavelet basis. And if you're wondering, the wavelet basis is the mathematical framework behind your high definition television sets. I know that the formula here is quite confusing, but it's the best I can come up with to create functions that have this digital-like behavior. So we see that orthogonality in functions is all about the inner product. And I want to talk about consequence of orthogonality. One of which is being able to describe the best approximation. What do I mean the best approximation? Well, the best approximation can be intuitively understood as a mathematical approximation that gives you the closest to your desired mathematical object. When I say closest, that means that I have to use some kind of definition of a distance. And if you discussed in your linear algebra class, you may remember concepts like a least squares approximation and its connection to orthogonal projections. So in essence, the discussion that follows is just the extrapolation of all of those concepts onto the spaces of functions, in particular the space L2. So for the rest of this discussion, I'm going to assume that I have an orthogonal set of functions. And this orthogonal set will be acting as a basis for subspaces. And if I take a finite subcollection of these functions and create a span, meaning I take all possible linear combinations of the functions phi k of t, where k will go from, say, 1 to n. So what do I mean by best approximation? Well, suppose I have a function Pn that belongs to my span of a finite subcollection, and that's a sum of some coefficients times the function phi k of t. And that Pn gives us the best approximation in the sense that the distance between f and Pn is less. In other words, it's a minimum of all possible distances between f and phi that can be created with any function from the set phi n. So in essence, I tried all possible functions from the span phi n that I created, and the one that gives me the smallest distance is the one that I call Pn. Then what happens is the difference between f and Pn has to be orthogonal to any function from my set phi n. In other words, f minus Pn in inner product with any phi should be 0 for any phi within my space phi n. In a linear algebra, you had a geometric interpretation of this, that if you have a point above a plane and you want to find the closest point on the plane, then you really have to construct a perpendicular line to the plane, and where this perpendicular line with the plane intersects, that's the best approximation. And it also gives you the smallest distance from any point on the plane to the given point that you have. The orthogonality implies a Pythagorean theorem-like identity, that the norm of f squared is the same as the norm of its components, which is the norm of Pn squared plus the norm of the difference. And the coefficient ck that I have in this decomposition can be computed by taking the dot product of f, phi k, and divide it by the norm of phi k squared. This is exactly the same expression for basis vectors in the spaces Rn. And that comes with no surprise, since orthogonality inherits the same properties. The proof is going to be quite involved, and the proof is completely optional. So if you want to, you can skip ahead and go for the next theorem and the discussion of the results. The proof can be broken into several steps. One of them, which is the minimality of this equation, implies this equation. And backwards, if we have this equation, then we achieve the minimum. So suppose Pn is the one that gives us minimum. But let's assume that there is a function phi from the space phi n that will give us a non-zero inner product. Suppose the inner product of f of minus Pn and phi is non-zero, which means it equals some number beta, and that beta is not zero. Well, then what I'm going to prove, that there is a way to improve the distance between f and Pn. And in fact, f minus Pn is not the smallest distance you can have. The way I'm going to do it is I'm going to start trying subtraction from f, Pn slightly altered by the function phi. This is equal to the inner product of f minus Pn minus epsilon phi with itself. Which is going to be the norm of f minus Pn squared minus epsilon in the product of phi with f minus Pn minus epsilon conjugated inner product of f minus Pn with phi plus epsilon squared times the norm of phi squared. Suppose I take the number alpha greater than 0 and let epsilon to be alpha times beta. Then the above equation equals to f minus Pn squared minus alpha times beta. And we can see that this is exactly the complex conjugate of beta, so it's times beta bar minus the complex conjugate of epsilon is going to be alpha bar times beta beta. But since alpha is a positive number, alpha bar is the same as alpha plus epsilon squared times norm of phi squared. So this equals to norm of f minus Pn squared minus 2 alpha norm of beta squared, and epsilon squared here can be replaced with alpha squared beta squared plus alpha squared norm of beta squared times norm of phi squared. So in fact we have a quadratic equation in terms of alpha, and when alpha is 0, this term that I'm going to highlight is exactly 0. Since every quadratic equation has two roots, then there's going to be another root for some positive value of alpha. So therefore any value alpha can take in between those two roots will make this particular number negative, and therefore for some small alpha the expression minus 2 alpha norm of beta squared plus alpha squared norm of beta squared times norm of phi squared will be negative. And therefore, for some value of epsilon, Pn plus epsilon phi is going to give us a better approximation because this norm of this difference is going to be smaller. Let me repeat it again. We assume that f minus Pn is the smallest norm possible, and then we altered our Pn a little bit, and then we went through the computation and arrived to the fact that this norm is the norm of f minus Pn minus something. That means that f minus Pn squared is not the smallest possible norm. But we assume it is smallest. Therefore our assumption that there is a function phi which gives us non-zero product here is an impossible thing to achieve. Let's try to prove it backwards. Now suppose that f minus Pn phi is 0 for all phi in phi n. We're going to prove that norm of f minus Pn is going to be smaller than any other possible norm. So suppose we take another p from the space phi n, and let phi to be Pn minus p. So the norm of f minus p squared can be written as the inner product of f minus p with itself, which is the inner product of f minus Pn plus Pn minus p with itself. So in a way, it's the inner product of f minus Pn plus phi and f minus Pn plus phi. This can be written as the inner product of f minus Pn with itself plus the inner product of phi with f minus Pn plus the inner product of f minus Pn with phi plus the inner product of phi with itself, which I can write as the norm squared of f minus Pn plus, well, these two are conjugates of each other. When you add two conjugates, the result is two real parts. Well, given that we assumed that any such dot product is zero, we get that this has to be the norm of f minus Pn squared plus the norm of phi squared. And therefore, no matter what p we take, the norm we have right here is going to end up larger than the norm of f minus Pn. And the only way for us to achieve the same result is to make phi 0. So in a way we have shown that f minus Pn is the smallest possible difference we can achieve within phi n as a set. Now, how do we prove the Pythagorean identity? We take the inequality that we just proved, that norm of f minus p equals the norm of f minus Pn plus the norm of phi, which is p minus Pn. By making p to be 0, we get that the norm of f squared equals the norm of f minus Pn squared plus the norm of Pn squared. As I said in the beginning of the proof, Pn should be the linear combination of the basis functions from your set. So how do we compute these coefficients? Well, we do know that f minus this sum in inner product with any function from the set, and I can take any basis function, should be 0. Therefore, the inner product of f with psi j minus the sum k goes from 1 to n of ck times the inner product of psi k with psi j should be 0. But only one of these inner products is going to be non-zero, namely the inner product of psi j with psi j. So we get that the inner product of f with psi j minus cj, inner product of psi j with itself, should be 0. This is also in the formula that cj as a coefficient should be the ratio of the inner product of f with phi j of t divided by the inner product of phi j with itself, which is the norm squared of phi j. And this concludes the proof of this theorem. Another result that is quite important is that the norm of your approximation can never exceed the norm of the function it approximates. And that leads to quite a few and interesting results. So the norm of Pn, since everything is orthogonal, is going to be just the sum, k goes from 1 to n, of the absolute values of ck squared times norm of psi k squared, which is the same as the sum. The absolute value of ck squared is going to be the absolute value of the inner product of f with phi k squared divided by the norm to the fourth, which then cancel out with the norm squared, giving us the norm of phi k on the bottom squared. And this summation is always going to be less than or equal than the norm of f squared. And the equality will hold if and only if f is the same as Pn. And since the norm is the upper bound for this summation, then we can say that this summation, even if we start to include more and more functions into our set phi n and into our basis, then this summation will never exceed the norm of f. And this result of this summation is always bounded above by the square of the norm of f, means that this summation will always converge even if we let it run to infinity. So these infinite sums are always going to be convergent. In fact, they're absolutely convergent, and they satisfy the so-called Bessel inequality. That if we have an infinite basis and we compute all those coefficients and add all these approximations, we still will never exceed the norm of the original function f. And the equality will hold if and only if f can be expressed exactly as this infinite sum The proof is much shorter, because we derived the equality that the norm of f squared equals the norm of Pn squared plus the norm of the difference. We say that the norm of f is always going to be greater or equal than the norm of Pn, which is equal to the inner product of the sum of ck, phi k, k goes from 1 to n, with the sum and doing these inner products, all of the functions that have different indices will result in the products being 0. So the only thing that resides here is the sum of ck in absolute value squared times the norms of phi k squared. K goes from 1 to n. Therefore, we have proven this inequality right here, and also this result, that this sum is convergent, because this sum is the sum of positive quantities. So the partial sums is an increasing sequence, and any increasing sequence that's bounded above must be convergent. So if we start adding up infinitely many terms, we will never be able to add more than the norm of f allows us to, and thus this sum must be convergent. And also we can see that the equality is only achieved if the norm of f minus Pn is 0. Or if it converges to 0. And then the norm of f squared will be equal to the norm of Pn squared. But the norm being 0 means that the difference is exactly the 0 function. and the f is exactly the same as Pn. For the infinite sums we have to consider the limits. But I'm not going to go into this much detail, and I'm going to leave this proof as it is. One last thing that I want to discuss is the question of completeness of our orthogonal sets, and the way we create the basis to represent all possible functions in our space. If we have an orthogonal set, can we call it a basis? In other words, can all functions in my space L2 from A to B be represented exactly by linear combinations or perhaps infinite series of functions from a basis? And if the answer is yes, then such an orthogonal set is called a complete set. In other words, completeness is the property that allows the orthogonal set to represent all possible functions from your space. And I want to just state the theorem and not bother with the proof of it, that the completeness also is linked to orthogonality. The orthogonal set is complete if and only if, for any function g in my space L2, the fact that g in inner product with phi k equals 0, and I mean all possible inner products with all possible phi k, implies that g must be a zero function. This is how we can understand this. If g is a non-zero function and we have a complete set, then there will be a basis element that will give us a non-zero dot product. And if all dot products are zero, then we must be dealing with a zero function. If it is possible to find a non-zero function, yet all of the dot products with all of the basis functions are zero, then we don't have a complete set, which is illustrated by this example. The cosine series is a curious one. It is a basis on the interval from 0 to pi, as the discrete cosine series is a thing in the Fourier analysis. However, on a set from minus pi to pi, it is not a complete orthogonal set. I'm going to skip the proof that this set is orthogonal. I'm going to go directly to using this theorem to show that this is not a complete set. I'm going to say suppose g of t is an odd function. In other words, g of minus t equals to g of t. Then the inner product of g with the cosine of kt is going to be the integral from minus pi to pi of g of t times cosine of kt dt, which can be broken into two integrals. One integral from minus pi to 0 of g of t times cosine of kt dt, plus a similar integral but from 0 to pi I'm going to flip the first integral. I know that t is negative. I'm going to employ change of variables in the first integral. I'm going to say that tau is negative t, and then dt is negative d tau, and the tau of 0 is 0, and the tau of negative pi is pi. So in essence, I'll be integrating from pi to 0 of g of negative tau cosine of negative k tau multiplied by negative d tau, plus an integral from 0 to pi of g of t cosine of kt dt. Now I'm going to use the fact that g is an odd function, and therefore g of minus tau is minus g of tau. Cosine is an even function, so cosine of negative k tau is cosine of k tau. And minus d tau also brings another minus. And when I flip the limits of integration, I'll get minus with another minus with another minus, integral from 0 to pi of g of tau cosine of k tau d tau plus the integral from 0 to pi of g of t cosine of kt dt. And as you can see, the first integral is exactly the negative of the second, so this result is always 0. So the inner product of my odd function g with any function from my orthogonal set cosine of kt will result in a 0 integration, in a 0 inner product. But g may be a non-zero odd function, and therefore the set of cosine kt is not a complete set. So this concludes the material for today. Before we finish, I'd like to go back and talk about what kind of properties of vector spaces we extrapolated today. So we have seen that the functions can be added to each other multiplied by constants. So we can make linear combinations, and we can make spans of functions. And we can make function spaces and function subspaces. We define the inner product, which works somewhat similarly to the inner product between the two vectors from Rn. Once you have the inner product, we define the orthogonality as the situation when the inner product is 0. Once we have orthogonality, we can start with orthogonal projections. And orthogonal projections are computed in exactly the same way as you computed them in Rn. It's just a formula with the dot products and the norms. And the best approximation is given to us by the orthogonal projection. And in fact, if you looked at the proofs of all the results that I talked about today, the proofs in the case of Rn spaces are exactly the same conceptually as the proofs that I talked about today. I haven't given you the proof of the Schwarz inequality, but this goes outside of what we need for this class. Let's just have trust in the mathematicians of past centuries. I proved the triangle inequality. And I proved the theorem that the best approximation is given to us by the orthogonal projection. In the orthogonal projection, the coefficients for the orthogonal projection are computed by a familiar formula that you may have seen in your linear algebra class when you talked about spaces Rn. The proofs were a bit technical, and the reason I give you the proof is so that you have some idea of how these things might be proven. In the cases when you start having infinite bases, convergence is a big issue. And this theorem for us is important as we start talking about infinite series that involves sines and cosines and other basis functions. And we need to be absolutely certain that we're not going to run into any convergence issues. This theorem relieves us of any worries. We can just be absolutely sure that the series that we construct will always converge. And the last theorem that I gave you today is the result that covers completeness. It's just the ability of a orthogonal set to represent all possible functions from your space. We need complete orthogonal set to form a basis. And although this theorem will not see much use, I want you to understand that for any basis we consider, this theorem has been used to show that the basis is complete. The last thing I want to add today is that this kind of mathematics is always playing a role behind the scenes when you're using any kind of advanced integral techniques. With the Laplace transform and the Fourier transform, it had to be rigorously constructed to show that you're using your integrals properly. So the ease with which we can solve initial value problems is coming at a price that someone sometime a few centuries ago has to grind through this kind of mathematics to prove that these techniques actually work. For us, we just get to use the fruits of their labor. For the rest of the class, I will probably mention these results in passing and will not concentrate too much on them. Thank you for your attention, and I'll see you in our next video.